Only cover.
I'm just saying you want to straight at the beginning, you're straight. I'm just saying that.
30 seconds. Hello, everyone. Welcome to today's seminar. So we are great to welcome our speaker, Rishi Sonthalia from Boston College. Now he's an assistant professor over there. Before Boston College, he was doing his PhD in Michigan, University of Michigan, right? Yeah. And then he go to UCLA, the postdoc, right?
Yep.
Yeah. So let's welcome our speaker.
Thank you. Thank you for having me. Really glad to be here. So I know the title says Universal Approximation of PDEs, but I won't be talking about very specific PDEs. Not going to be general ones. Just for some motivation, recent work, people have looked at using neural networks to solve all sorts of different types of PDEs. Two common techniques are physics-informed neural networks, and this other one called neural operators. These work by taking in the equation and an initial condition and give you a solution. Here, I'm not going to develop sort of any new techniques. What we're looking at is trying to prove some theoretical guarantees about these networks, especially when we apply them to PDEs. In particular, we're going to care about two different types of guarantees. The first one is how big the network has to be able to approximate a solution to a given epsilon. And then if we actually try to train these networks, what the loss landscape might look like. Okay, and if anyone has any questions at any point, please stop and ask me. Okay, so like I said, we're going to be looking at two very specific PDEs. The details, I'll go over them again later. Just as an overview, the first one will actually be mean field equations. The mean field equations, if you haven't seen them before, you imagine you have some particles that are evolving, and somehow they're permutation invariant. And so when you send the limit as n goes to infinity for the number of particles, you can just think about it as a measure evolving in time. And the other one will be just the Laplace-Beltrami equation, right? So you have your Laplacian on the manifold, and we just want to find some eigenfunctions. Okay, so the first one I'm going to talk about is mean field equations. This is going to be worked with two collaborators, Shiba and Karthik. They're both postdocs now at LNAL. I would put an archive link up for the paper, but it's on hold for some reason. So I will have a link hopefully soon. Okay, so just some examples of mean field dynamics. So people have seen like birds flocking. One example, right? Each particular bird is not too important, but there's a nice dynamic for the full flock. Similarly with fish, cars, or even drones. Okay, so let's look at the math a little bit closely. So we're going to imagine we have some omega, which is a subset of RD. You can think about it as being compact, but for some cases, we might not need it to be compact, but compact is good. The curly script P is the space of all probability measures on omega. So we have this vector field F that takes in a vector and a measure and outputs a vector. Right, and the mean field behavior of interacting particles can be sort of described by this equation, right? dZdt is just given by this vector field. And so this vector field is what we're going to try to approximate using a neural network. And then you can see that the measure evolved as a solution to the following continuity equation, right? So d mu dt plus something is equal to 0, right? So we're going to have sort of two steps here. First, we're going to use a neural network, in particular a transformer, to approximate F. And then we're just gonna give your favorite solver this approximation for the gradient and have it sort of like figure out how the measure evolves in time. All right. So before we get to the math, I want to show some nice examples that it actually works. So the first equation we look at is the Cocker-Smale equation. So this is what governs sort of like flocking or fish milling, that sort of stuff. So we will consider something simple. We just have a particle in R2, and we have its velocity as well. So we care about this 4-dimensional vector, which is its position and its velocity, sort of how it evolves in time. In particular, there are equations, you can write it down, right? So the vector field is supposed to be the derivative. So the derivative of the position is the velocity, and then the acceleration is given by this system that tells you how the particles move. All good. Right, there's also a particle version, which is not the mean field version, right, where you measure, so this is an actual finite number of particles. Okay. So on the left, I give SciPy's initial value solving method, the true gradient from the actual math equations. On the right is what the transformer learned. And now I'm going to evolve sort of both of these in time. Right, and you can see these are sort of quite complex. Different things are moving at different speeds, they're overtaking, they don't quite all have the same direction. And you can see the transformer learned it quite well, right? And in particular, the next slide actually surprises me. If you run both at the same time, you can actually see how well it learned. Right, they're basically overlapping. And here all the paths sort of look straight. But I plotted some of the trajectories here, and you can see they're not straight, they actually sort of curve. Right, so the transformer can learn these complex interactions between particles, and they can be used to sort of evolve the equation in time. Yeah.
Within the birds after some time?
So the Cocker-Smale, I am told, I'm not a PDE person, is a consensus model. And so apparently they will get consensus toward the direction and velocity and sort of all move in that direction. That happens sort of eventually. I didn't show that over here. This is more the initial bit, which seemed more interesting than them all just moving in a straight line.
I think the question is whether red and blue will diverge in the tech.
Whether red and blue will diverge, yes, they will eventually diverge. You can see it here actually, so might be difficult to see it, but here you can see sort of the gray line, they're separating. So like I'll show some more plots, but as you evolve time more, they'll sort of get further apart. Okay, here's a second nice example. So consider like a 2-layer neural network, right? So it's given by that equation. Yeah.
Sorry, we already discussed, what do you mean by learning? What's your setting? What's your data?
Yeah, so right, so the neural network is trying to learn this. So I give an input example. So in particular, I train it with the particle version. So I give it x's and v's, and output pairs as the derivatives.
So do we have data or not? We have data for training.
Yes, this is synthetic data. We also did it with real data, the fish milling data set. But there we can't give it a new initialization because we don't have the fish. But here we did train it on, I think, like 20 or 50 different initializations and for like 100 time steps. And then this was a completely new initialization.
Yeah, so the input to network is the x and the v.
Yeah.
The output is f.
F of x.
Fx of v.
Yeah.
So do we have data for f?
Yeah, so I synthetically created, right? So I have the equation. I can.
Okay, so you're not discovering f, so you just have the process for f.
You have, yeah, you have input output.
Oh, okay.
Yeah. Similarly, here's another example with 2-layer networks. Here you can think about the particles as being these weights. It was showed by May and Montanari in 2019 that you can think about training a two-layer network. It had a corresponding mean field equation. The psi depend on the learning rate schedule, and speed, which is similar to the F, and this complicated expression that depends on the data. Not too important. I just wanted to show that we can learn it. So on top, we have the heat map of the parameters. On the very top, you can see the epoch number. I'm going to hit play in a second. What you will see is that the parameters actually don't change very much. This is an unfortunate thing about neural networks.
So wait a second, they treated the parameters of the neural network as the objects that are changing
Yes,
as you learn on some
yes.
data set. For large N, those parameters themselves obey a mean field evolution equation.
Yes.
Got it.
Then you're using some other network called transformer
Yes,
to mimic, which also requires a training.
yes.
It also would have mean field theory dynamics.
In principle.
All the way down.
I'm going to play. So unfortunately, the parameters don't change much, even though it's a tiny network. But here you'll see that the change, this is the total sum of the gradients. The change is, you can see that a little bit more. Network 1 is actual learning dynamics. Network 2 is what the transformer simulated. So you can see that there are differences in this case. But it turns out it still learns a pretty good model. So if you plot like training loss, like it diverges a bit, but it does tracks it quite well. And if you plot test loss, it did learn a model that generalized. Okay. So that was a couple of examples to hopefully show you that you can learn these models using transformers. So a little bit of background on transformer, if you've not seen it before.
I asked, what was your dimension of the neural net there?
So it's a 10, so it's a 10, so here the x's live in 10-dimensional space, and capital N is 100.
Yes, so the W dimensionality is only moderate.
Yeah.
It's interesting to know if that then became 1,000 or 1,000,000, does it break down, or is it still working?
Yeah, that would be interesting. So the 10 to 100 was the bigger example, right? The previous one was like 4.
Yes.
So this one, I'm trying something a little bit bigger.
I didn't know.
Yes.
Okay, I'm gonna ask this
Yeah.
now
Yeah.
instead of at the end.
Okay.
Do you have an example that doesn't work?
I don't, and we have theory that says it should work. Yeah.
So here you actually have you tried as Adam or other cases?
This was just simple as you.
Okay.
Okay, so these were approximated using a transformer. Here's sort of a transformer architecture if you haven't seen it before. It takes in a sequence of vectors. They're arranged in a sequence, but the actual sequence structure is not important. So you can think about it as a set of vectors. It has a self-attention layer, which I won't go into the details. There's a layer normalization, which we're actually going to ignore because add complication, a regular feed-forward layer with some residual connections. Right? This is what a transformer network looks like. And one very important thing is they are permutation equivalent. Right? So this is why I don't like thinking about these as a sequence, because if you permute x1 and x2, all it does is permute y1. Right? So the permutation equivariant. So I like thinking about them as like sets of vectors to sets of vectors.
So they do not have a position equivalent.
No position. Yeah. Right. So there's some nice universal approximation results that have been proved previously about transformers that we're going to strongly leverage. So this paper by Alberti et al. From last year, where they proved this really nice theorem, which said let F be any permutation invariant equivariant map, and let epsilon be bigger than 0. Then there exists a transformer such that in like the uniform norm, you have a bound of epsilon, right? So this is quite strong. In particular, they proved even more things, right? Like the depth of this transformer is 4. It's 4 layers. They bound the width of the attention layer as well. Width is bounded by like 2 times d, which is the input dimension. This is really nice because both the width and depth are now bounded independent of epsilon and n.
It sounds like,
The sequence line.
overall ignorance of theorems about representing continuous functions
Mhm.
exactly
Mhm.
by compositions of about that size.
Yeah,
Does it leverage that?
it actually does. So basically what they do is they create an embedding layer very explicitly. They write down the attention layer very explicitly. And then they say the output of this is a continuous function. These other constructions exist that can approximate it, just add it up. So that's basically what their proof is. Okay, so here's if you're paying attention, the small, minute detail. So transformer acts on finite dimensional spaces, right? They take in finite dimensional vectors and a finite sequence and give you an output sequence. This vector field acts on an infinite dimensional space, right? It takes in a vector and a measure, right? This measure lives in an infinite dimensional space. So we need to do a little bit, if I want to say transformers approximate these objects, right? Because they're not even acting in the same space. So there has been some work. There was this paper by Geszkowski and all from last year, where they defined a continuous version of attention. So these are things, so these are then objects that do act on this space. The way it's defined is you take your input X and you compute the expected attention, and the expectation is with respect to that measure. And there's this paper from this year, actually, like about a month ago, that proved universal approximation for these objects. But here we're going to talk about hopefully a slightly simpler object. And we can leverage things that we already know about finite dimensional transformers. Okay, so here's what I call the expected transformer. So we just take a transformer that works on some sequence length, let's call it n. And I'm going to define this expected transformer that now works on this infinite dimensional space. And it's very simple. All I'm going to do is take an expectation. Right, so what I do is I sample n points from my distribution. I give the transformer all n plus 1 point, right? So the original x plus the new n points. I compute I take the output that corresponds to x, and I just compute the expected value. Right, so this is quite simple. It's just you can do the transformer a bunch of different inputs and see what the average output is. Right. And what I claim over here is that this object will well approximate our vector field. Okay. So to be able to state the theorem, I'm going to need some assumptions on the vector field. So in particular, I'm going to need it to be Lipschitz. And what does it mean to be Lipschitz with respect to measures? Well, I need a metric in the space of measures. So I'm just going to use a standard one, which is if you have 2 measures, the sub p means the pth moment is finite. Right, so if I have 2 measures, I can just define the Wasserstein distance. Right, so here pi is a set of all couplings. Right, so the marginals are mu and nu, and then you just compute this. Right, d here is a metric on omega. Right, what's really nice about this is if omega is compact, this thing metrizes weak convergence. So which means if you have a sequence of measures that weakly converge to something, that's the same as saying the distance between the 2 measures. Distance between mu n and mu sort of goes to 0. And in general, if we have this metric p, if we have it for bigger p, it's a stronger metric, right? So if we have convergence in p, then for q smaller than p, we have convergence in that one. Okay. So here's our theorem. Right, so we let epsilon be bigger than 0. We have some n. We have our compact set. We have our vector field f that is Lipschitz. right? And for some given Wasserstein metric P. Then there exists a transformer, right, with depth 4, like I said, the same width as before, and we get sort of this approximation. So this approximation, right, I'm going to break it down in a second. With a proof sketch to see where the terms, yeah.
What's Q?
So Q is actually sort of like how many moments you have. So in general, we can think about for our, it's not in the statement here, it's one in the paper, the actual statement doesn't quite fit. But Q is sort of how many moments you have in for the measures. In general, you can think about Q as just being quite large, because we are working on a compact set, so you actually have all moments.
But if I wanted to use P equal 2, I can use Q equals 3.
Yeah, that'd be fine, yeah. In general, actually, it's like, so the optimal P is actually, I think, like D over 2 plus 1.
Ah,
Right, so you want higher P's, right? So you want to be Lipschitz with respect to a stronger metric. But going more than D over 2 plus 1 doesn't give you any benefits in the
Q would be bigger than Q.
yeah. Yes, Q has to be bigger than. Yes. Okay. So here is a quick proof sketch. The proof for this one is not too difficult. So we're going to need to define a couple of things. So given our particles, C1 to Zn, I'm going to use nu sub z of n to just denote this Dirac delta measure, right? So it has a Dirac delta HZI. And I'm going to use this not curly f to denote sort of this vector that it just evaluates our vector field at each of those points with this measure. Right, so this function is now some nice permutation equivariant function. So we can do the following. Right, so I look at the difference between the transformer and my vector field. We're using suit norms, so I can just write it out. I'm going to replace the expected transformer with its definition that came from an integral. Right. I can pull the vector field into the integral. It doesn't depend on what I'm integrating. Integrating as a probability measure. I'm going to change the equality to an inequality and pull the norm in. Standard analysis. I'm going to focus on the integrand. Right? So just look at that. Continuing with more standard analysis, I'm going to add and subtract a whole bunch of things. Yes, right. So here, and then I'm going to use the triangle inequality and break it up. Right. So here, this is the difference between the finite transformer and this permutation equivariant map I defined. So this we can just bound using the results from Alberti, right? There's a transformer such that this is well approximated. This is where we get our epsilon term from. This is now the difference for the vector field, where the x input is the same, but the measures are different. Right, so here's the Dirac delta measure at n plus 1 points. Here's the Dirac delta measure at n points. This has one additional extra point. I can just use my Lipschitz assumption to bound it by something like this. Maybe there's 1 over p I'm missing somewhere, but you get some nice bound. This one, I now have the nu, which is my finite approximation of mu, Dirac deltas. I can again use my Lipschitz assumption and bound it by this object, which is the Wasserstein distance between the finite approximation and mu. And quantitatively bounding that is actually quite difficult. And we found a paper from last year, like a pure math paper, that bounds it, which gives you your rate over here, right? So this whole term, this C with respect to the Lipschitz constant, and this just comes from that term. Everything else is just the answer. So, yeah. So there we go. So that shows you can take a transformer and approximate the vector field. But approximating the vector field is not everything, right? We want to also be able to show that if we evolve the system with our approximation and with the true equation that they don't deviate too much. Right, so to be able to solve the system, we have this notion of a continuity equation, right, which with a solution. So there's this idea of a Lagrangian solution, which is just given by this integral operator, x plus its integral. And the actual definition, not too important. Due to the Lipschitz property, right, we can show that there is a unique solution to this Lagrangian, the unique Lagrangian solution. So there exists a unique solution to the original equation, but we don't know whether the transformer is Lipschitz. Right, we can prove the transformer is close, but it need not be Lipschitz. And actually proving its Lipschitz is quite challenging. The constant normally depends upon the depth. But here we have bounded depth, so it should be okay. But to simplify things, we just assume it has a Lagrangian solution. Okay, right, so the Lagrangian solution to the transformer. All right, then we can prove this theorem. So again, we have that our vector field is Lipschitz. We need it to be bounded above by this constant. Here, M1 is the first moment. And we need this map X to this to be C1. Need some nice smoothness assumptions. We also need our initial distribution to have sort of bounded support. We can't have like unbounded support. Then we construct this compact set such that our finite time evolution has to stay in this compact set. Then we can apply some standard techniques. I won't go over the proof, and show that the distance between the true measure and what we get from the transformer is bounded above by this. So this term grows like an exponential. Right, so there's a bound. And so if tau is small, you can see that this thing is probably good. But if tau is large, you might not be approximating. Other things to see, right? The better you approximate the original thing, the better, the longer you'll be closer together. Also, the larger P you have the Lipschitzness for, the stronger metric you'll get the approximation. Okay, and to just talk about how someone asking about whether they diverge. So here's the L2 distance between the mean L2 distance between the true Cocker-Smale X, and then U is the velocity. So here the solid line is the median over like 100 trials. The shaded region is the interquartile range, the 25th to 75th percentile. You can see as we sort of evolve time or increase time with sort of diverge. In particular, if you go further away, right, the deviation also increases.
And you kind of start over.
So each trial is we sample an initial condition and we run it to time 3. Then we sample another initial condition and run it to time 3.
Yeah, I'm just wondering, is there some way to refresh it?
We did not try that, right? So use the end time as a new initial condition and restart.
Yes.
That was a good idea. We did not try. We just were seeing whether we saw that divergence. What was happening? We also did this for the neural network. So here's how far the parameters are. You can actually see that it's quite small, 10 to the -4. But you can see that as you increase time, they do quite diverge. Any questions? Hopefully you can see that transformers can approximate some vector fields.
Well, you have the problem of training transplant.
Yes.
And that's very much a different question, right? People to do it and say they have it, but not mathematics. We don't have a demonstration of a proven training algorithm.
Yes.
I have a suggestion.
Mm-hmm.
Okay. So the problem here is that most people do it by an optimization.
Yes.
But the superior idea would be to choose a posterior distribution that would concentrate with a lot of data and evolve that a distribution from a prior to a posterior. But to do so, you would need to satisfy homofocal block equations, continuity equations. So the appropriate drifts or vector fields or solutions to specify different equations.
Mhm.
If you could get examples of what that function is, now you could use these techniques to, you know,
Yeah.
produce a solution to how to train a transformer.
Potentially. I will say in this case, I didn't have to do much tweaking. It just trained and I got losses on this order.
Right, but you don't have a theory,
Yeah, I don't have a theory. It
right?
just seemed to work, which is nice. Okay. So that was to do with approximating the mean field equation. Now we're gonna go to something hopefully simpler, like simpler PDE, Laplacian. And here I'm gonna try to present a little bit more theory about actually training the networks, about how we could train them and sort of what that looks like. Okay, so this is work with two other people, Chen Wei, the grad student in statistics at the University of Wisconsin, and Nicholas, who's an associate professor in statistics at the University of Wisconsin. This paper is up on the archive. You can find it. It's the archive number. Okay, so just as a refresher, we're talking about the Laplace-Beltrami operator, right? So we're going to assume M to be an M-dimensional compact manifold. I'm going to assume it's embedded in RD, right? So M is smaller than D. I'm going to have some function and a measure mu with density rho, right? And then we can write down the normalized operator for this form. The actual form is again not too important. And then an eigenfunction is any function that sort of satisfies this for some lambda. Right, so the goal over here is we're going to try to approximate f, which is an eigenfunction, using a neural net. Okay, right, and just for notation, lambdas with a superscript m will be the eigenvalues for the actual operator. All right, so just some examples if you haven't seen it before. So this M does not satisfy the assumptions I said before about being compact. But just if it's a real line, the Laplacian is just second derivative. Its eigenfunctions are just sines and cosines. And you have some of these things. A little bit more realistic example is you take the two-dimensional sphere. Here, if you use spherical coordinates, you can again write down the Laplacian. This is for a uniform distribution. And then you can explicitly write down the eigenfunctions as well. And here are sort of like nice pictures of it. Okay. All right, so what's the main question, right? So we want to approximate the eigenfunction. So if we know the manifold, we know the eigenvalue, and if we know the function, right, then approximating it is easy. Right. So you have all sorts of universal approximation results. It works. In practice, all we have is n data points sampled from the manifold, right? So we have n data points sampled uniformly from the not uniformly, sampled independently using some measure on the manifold, and we still want to learn the eigenfunctions, right? So if fi is an eigenfunction, we still want to train a neural network given just this data to approximate the eigenfunction. Okay. So the first issue is that the manifold is not known, right? We don't even know the manifold, we just know data points in the manifold. But this issue is sort of solved by prior work by Caldor and Trios. This is older now, 2020. And basically what they showed was if eta is some non-negative decreasing function, and you look at this sort of like scaled operator, right? So you take the norm, the actual Euclidean distance, scale it by some scale tau and pass it into eta. And you think about the g tau as sort of weights of a weighted graph. You can look at the graph Laplacian, right? Given by this. Right, this normalized graph Laplacian, some nice positive semi-definite matrix. And you can take its eigen decomposition. You can think about the eigenvectors as functions on the data points that you do have, right? So these are what it looks like as a function. And what they prove that as n goes to infinity, sorry, this should be a tau, and as tau goes to 0, you have that these eigenvectors actually converge to the eigenfunctions of the Laplacian on the manifold. So what do we have to do? Well, we take our data, we pick a tau, we create this graph, we compute the graph Laplacian, and then we just need to factorize it, right? So we just need to factorize this matrix using a neural network. So there's been some prior work on factorizing matrices using neural networks. The paper by a bunch of people here, where they used constrained optimization to factorize the network. There's this other paper that we're going to look at more, which is a little bit more recent, where they define a spectral loss function, and they show some equivalence with the contrastive ring. We're going to analyze mostly this loss function. So what is it, right? So let f theta be our neural network, right? Theta will represent the parameters. I'm going to define y theta to be the matrix you get when you pass in your data to the neural network. And here R will be the number of eigenfunctions you want to approximate, right? So we want to approximate the first R eigenfunctions, right? And in general, given some positive semi-definite matrix that we want to factor, if we're doing it for the Laplacian, we consider this version, but slightly shifted to improve its conditioning. And then the simplest loss function, you want to do y transpose minus your positive semi-definite matrix and compute this for being useful, right? But this, even without the neural network parameterization, already has some challenges, right? Because you have a y transpose, it's not convex, right? So you have non-convexity already. And the other thing you have is sort of, let's say y star as a matrix is a solution. You can pick any rotation matrix and multiply from the right, you get another solution. So you have sort of at least two challenges before you even think about the parameterization that comes in from the neural network. Okay. So let's think about just a simple picture about what's going on. So this slide is your space of functions. You have your eigenfunction somewhere way out there. Here is your neural network function class that exists, right? We want to approximate that function by something in here. Here is where the optimal y star is, right? So this is a critical point of the global minimum. And potentially we have, due to non-convexity, we have all these saddles scattered around. So we first start by saying something about what these saddles look like. So what we show first is that with high probability, you can write down what the eigenvalues of the AN looks like, which came from the Laplacian. And you can see you have this sort of constant order term, and then you have this quadratic order term in tau, right? So in particular, if you take any two eigenvalues and look at their difference, and take the square root, right? It's on order tau, right? So in particular, the Frobenius norm distance between any saddle point and your optimum is on order tau. This is not good. So if you go back to our cartoon, it doesn't look like this. There's actually some ball of size tau, and everything is in there. Right, so you have a whole bunch of saddle points that are near the optimum. Okay, so the first thing we show is sort of this universal approximation result, which says high probability, there exists a ReLU network. I'll tell you how deep, how wide, and how big the weights can be, such that the y theta you get from the neural network, and the optimal one is now within distance tau squared, right? So it's a little bit closer, right? So we know it's actually close to the optimum, and it's not sitting somewhere near some other saddle point. And then this is for the actual data that we got x1 to xn. You can then lift that to saying how close the network is compared to the true eigenfunction and bound that as well. We lose a little bit, right? We go from tau squared to tau, but the norm also went from the Frobenius to the L.
Can you say something about the relationship between the width and the epsilon?
Yes. So you can bound the depth. The depth scales like 1 over log 1 over epsilon. The width scales like 1 over epsilon to the m. M is the dimension of the manifold. That is terrible.
But
But it is better than the 1 over epsilon to the d, which is the ambient dimension, right? So we can go from the ambient dimension to at least the dimension of the map. And then we can also bound how big the weights have to be. That one is not too important. Right, so if we go back to our cartoon, so we can imagine that the saddles are, let's just zoom in a little bit, the saddle's a little bit further away. There's some smaller circle. Our y theta lives in there. And our eigenfunction is not way off to the side. It's actually somewhere close by.
if you switch to using your transformers where you had the width like twice the dimension, could you improve?
So for the transformer, the width, that bound was only for the attention layer. For the feed forward layer, the width was not actually bound.
Oh, they were wide.
Yes, those could be wide. Yes, that's only for the attention. Okay, right, did I skip ahead? Yeah, okay, so this tells us there exists some y theta that's close by. But that y theta is not necessarily the actual optimal global, like if we solve the problem, that's not where the global minimum is, right? So we want to say something potentially about the global minimum. And we actually need our previous theorem to be able to say something about this. And in this case, we get something of this form. Again, we have the tau squared. That is nice. So in particular, if we go back to our cartoon, right, so we not only have the y theta from before, we also have this f theta stuff that also exists in here. All right, so now I've told you that there is this formulation where you can take data, create a loss function, train a network, and the global optimum of that loss function is a good approximation for what we want. And there are some rates about how big that network needs to be. But that still doesn't tell us anything about the actual training. Right, so if we train the network, right, we've shown that such a network exists. Finding it, different problem. Traditionally, we find networks using gradient descent, right? So gradient descent for a nice convex function, very simple. You start somewhere, or you just keep going down until you hit the bottom. Right, but we have non-convexity. We actually don't, well, the parameterization of the network couldn't include local minimums. Right, so you could go down and you could get stuck. Not good. Okay, right, so again, as our cartoon, we have the red dot, which is our initialization point. We can start training, it's going quickly, and then it slows down, it gets to a saddle, and sort of gets stuck. Right, so this is something that might happen. So we want to say something about this. We can't quite say it for like a general parameterized neural network, but we can say something about the ambient problem, where we think about it in the space of sort of functions rather than in the parameter space. Right, so we need this notion called geodesic convexity. Right, so a subset of a manifold is geodetically convex. If for any 2 points, there's a geodesic that connects them. So a regular sort of definition of convexity on a manifold. And then we say a function on a convex set, it is geodesically convex. If for every unit speed geodesic, this composition is convex in the regular sense. Right, so this function goes from 0, 1 to R. So the function from R to R, so we can talk about it as convex. What's nice about geodesically convex functions is if we do, say, a Riemannian gradient descent on this manifold, on the set, then all local minima are global minima. Right, so we have all the nice things in convexity, and we don't have to worry too much. Okay, so let's think about our problem on a manifold. In particular, the manifold we're going to do is we're going to look at the space of matrices, and then we're going to quotient it out by the rotations, right? So remember, if y star was a solution, and y star q was also a solution. We don't like that. So we're gonna look at this quotient manifold where we sort of quotiented that out. And here's our loss function on that manifold. And assuming there's an eigengap between the R and the R plus first eigenvalue, right? We show that the loss landscape is sort of benign. And when I mean benign, sort of one of three things happen. You're either far away from any critical point, in which case you have large gradients, which is great. You make lots of progress very quickly. If you're near a saddle point, your Hessian has a negative eigenvalue. So this means there's an escape direction. So when you get close to a Hessian, there's a direction around which you can sort of squiggle away. And then once you've escaped from your saddle points and your neighborhood of the true solution, it's geodesically convex in the neighborhood of the true solution. All right, so ideally what happens is you start somewhere, you move very quickly, maybe you get stuck near a saddle for a little bit, but then you escape it, and then you eventually converge.
Presumably, all of those discussion points are functions of that eigengap.
Yes,
Yeah,
the size of each of these regions and how big.
yeah.
So in the paper, we can quantify how big the magnitude is. We can quantify how large the negative eigenvalue is, and that's all a function of the eigenvalue. Okay. Right, so what actually happens, we go back to our cartoon, or what we hope what happens is we start training quickly. We get to our saddle point, we no longer get stuck, we somehow squiggle around, and then sort of smoothly converge to our global optimum. Okay, so let's see if this happens in practice. I'm going to try this on two simple examples. First, I'm going to sample sort of 2000 data points uniformly from the two-sphere embedded in 3 dimensions. I'm going to construct a 30 nearest neighbor graph. I'm going to train one hidden layer neural network. It's quite big, so don't worry about whether the width and all of that. It's 10,000 hidden neurons. I'm learning one eigenfunction. Right? Here are some details about how the network was trained. And here it is. So on the left is what you get if you actually factor the matrix using one of SciPy or NumPy or Torch's factorization libraries. On the right is what you get if you train the neural network. So you can see that the two are quite close. In fact, I'm not even sure if I can tell them apart, but they are different images. This doesn't quite look like a spherical harmonic, which is what the eigenfunction should be. But if you remember, we just say we're close to this, but this distance depends on how many data points we have and our scale tau. Okay. How about we try it for more realistic data, right? So there I knew the manifold, I knew the eigenfunction, I knew everything. Here I take data from MNIST, right? So MNIST, so the images live on some manifold, I don't know what it looks like. I create my graph Laplacian and I look at the ambient problem where I just train that with gradient descent. And I try two initializations, one where you initialize it near a saddle. And you see, right, the initial gradient norms are very small, but it very quickly escapes it. And we get to this yellow region where we have large gradients. And eventually we get to this purple region where we're sort of in the geodesically convex region. And these points are colored based on our theoretical boundaries, not on the actual values of the gradient model. Right, so they match up quite well. If I initialize far away from the saddle, we see these nice smoothly converge. This is for the ambient problem. What if I parameterize the neural network? So here's what it is for a two-layer neural network. Initializing it near a saddle was a little bit more tricky. I don't feel comfortable calling a gradient norm of 10 to the 3 a saddle, but this was the closest I could get. And it seems to have the same sort of dynamics, right? Where it very quickly gets to a point where it has really large gradients, right? So it sort of gets away from the saddle and then smoothly converges to a critical point. And if you initialize away from a saddle, what I think is happening here is, right, we're in our large gradient norm regime, we somehow get closer to a saddle, escape it, and then converge smoothly to solution. Okay, so in conclusion, neural networks can approximate solutions to PDEs. In particular, with PDEs, mean field equations, like we developed a framework, or we showed that they can be solved using transformers, and prove sort of these results for the expected transformer. And then for the eigenfunction, the Laplace Beltrami operator, we showed we can learn these and sort of be a theoretical bound here. And then the global loss landscape is sort of benign under these nice conditions. Here are the references. So here's the paper for the Laplace Beltrami. This one soon to be appearing whenever it gets off hold on our site. Okay, thank you. And questions?
Can you, I don't know if in your slide you showed that how the precision was related to the number of links that you had.
You mean in the empirical or
In both empirical and theoretical.
the,
Say you want the precision absolute, you put something, you need that one branch down to a point.
right, so this is sort of the size.
The width is. That's what-
We can actually say a little bit more. We can also say something about how many of the weights need to be non-zero. But I felt listing, it's a quite long expression, listing that didn't seem to add much.
Also a function of the architecture.
Yeah, this is just a regular feed-forward network with a ReLU activation.
So first of all, thanks for the talk, it was great. I have a question, so about this eigenfunction approximation, right? So it's kind of a very kind of nice setup, it's fairly contained, but I'm curious if you tried actually using these eigenfunctions for some downstream tasks, in the sense that, you know, like your own living, for example, has some nice work where, you know, you use it for generation and stuff, and over the sphere, and then this example that you gave, like, did you try like maybe learning 10, 20 of these eigenfunctions and trying to plug them in, you know, see how?
So we haven't actually tried. Most of what we were showing is just that, like, if you do what yeah, basically we're saying if you actually train a network using what their setup is, that there are some theory results for it. And so we're just showing how big the network needs to be and something about the loss landscape.
Right.
Yeah.
You were saying something about how the example you're comparing with when you train your network was something from a sci-fi library. It's interesting because that also, as you said, an approximation based on the points that are there. Correct?
Yes.
But like, I wonder what algorithm they're using, you know, because it almost says something, there's some kind of like, because these seem like very different algorithms, like there's no way that's similar if it's not using also like a similar kind of architecture. I mean,
No, so there is, so if you have a matrix that is positive semi-definite, right, it does have an IN decomposition.
right.
And there, I don't quite know I don't remember the names, but there are these like iterative methods that are proven to converge,
Okay.
right, to whatever precision you want.
Right.
And I know SciPy, I think, uses one of these, like where you keep raising the matrix to power and stuff.
Yeah, power.
Yes.
Okay, got it. Okay, sorry, I need to be reminded in terms of intrinsically what is actually computed there, yes.
Yes, so they use like these power methods, which I think used to compute this one, and then we use gradient descent,
Right,
and it seems to converge to the same solution.
okay, got it. You're solving the same problem.
Yes,
Yeah, so for this application, not solving a PDE, right?
You're not solving a PD, you're just factorizing a matrix.
Yeah, then, so for, the theory is good, but for the application side. So what's the advantage of this method here, or why, what kind of setting?
Okay, so the main advantage of using a neural network over the power method or something is this one, you actually need to write down the whole matrix. And so that's quite memory intensive, your matrices are large. Here, you don't have to actually write down the whole matrix. You can do like mini batch gradient descent, and it still converges to the same thing. And so you have less memory constraints. It's mostly a memory thing to use a neural network over power.
I think the standard way the fancy way to diagonalize a matrix, I think you transform it to upper Hessenberg first. and then you run like the QR algorithm. And I would be curious to know.
I think you still need to write down the whole matrix all at once, right? No?
Not if it's, so if it's upper Hessenberg nodes, then it's banded, it's quite sparse. And I'm trying to remember how to do the.
Could be full upper triangle.
No, I don't think, oh. Yeah, maybe upper
Which-
Hessenberg is, yeah, because it's got like one below the diagonal, yeah, maybe it is, yeah, I just wonder. I'm curious, like, when you can run these side by side,
Mhm.
how do they differ?
So I tried it. We upped the number. So this is 2,000 data points. I went up to like 20,000 data points, and neural network took minutes. SciPy took like tens of minutes. And so,
Yeah, and then just like as the innards of the algorithms,
Yeah.
like, what steps are they going through, where do they differ?
yeah, I haven't tried plotting out the internal. I was just timing it to see how well.
Yeah, and then like, oh, if you can do this with batches, then is there some way to do in batches, a different form of computing eigenvalues and eigenvectors? I guess there are Krylov methods as well.
But isn't that sort of all the same? Krylov, Heisenberg, power.
Yeah, they're all kind of, they all have slight differences, there's antidotes, there's this, there's only. Like, where do these differ from the textbooks full of?
Yeah, I feel like those methods are like very large jumps.
Yeah,
Whereas you're taking very local jumps.
yeah, I don't know, I'm curious how they're.
More questions?
One more question, we think our speaker again.